Okay, let's start the last talk for today. Ryo Fujita-san will talk about singularities of R-matrices and E-invariants for Dynkin quivers.
Thank you. So first of all, I'd like to express my gratitude to the organizers for giving me this opportunity to speak. So today I'd like to explain my recent work concerning singularity of R-matrices for quantum affine algebras. So first let me explain why singularity of R-matrices is interesting or why it is important. So motivation. Maybe I will spend the first 30 minutes for this motivation part, but anyway, so we will work with the following settings. So let G be complex finite-dimensional simple real algebra. So this is finite-dimensional complex numbers, and we take quantum parameter Q, which is non-zero complex number, and we assume that this is not root infinity, so it has infinite multiplicative order. And associated to this data, we get quantum affine algebra, or rather quantum loop algebra, quantum affine algebra at level 0. So here LG denotes the loop algebra. And this is a large hop algebra. But in this talk, we are interested in the category of only finite dimensional representations. And this category is actually very interesting monoidal structure. So this is a monoidal abelian category. And in the case of finite type quantum group, this kind of category of finite dimensional modulus form a braided tensor category. But in this quantum loop setting, so this is no longer braided. As tensor category. And indeed, there exists many pair of simple representations in this category such that they do not commute. Meaning that the tensor product tensor L prime is not isomorphic to the opposite tensor product L prime of tensor L in general. But interestingly, we can say that this is generically braided. Generically braided. So in the following sense, so we can freely deform one of the tensor factor L, for example, by using certain parameter which is called spectral parameter. So let us take some generic spectral parameter. Then we apply some shift. So this is a deformation such that if we specialize this parameter z equals 1, then we come back to the original representation. And after applying this deformation, we see that everything is commutative. So the tensor product, this tensor product is isomorphic to the opposite tensor product. So as representation of quantum loop algebra. And furthermore, So this kind of isomorphism is called R-matrix. And furthermore, if we fix a normalization, for example, so taking highest weight vectors of each representations, and we require the tensor product of highest weight vectors go to the opposite tensor. So this is highest weight vector. Then this determines uniquely, and this is what I call the normalized R matrix. In this talk. And this can be seen as a matrix valued rational function. So we see this as a so we consider this matrix space of matrices with finite dimensional vector spaces, and so this is matrix valued rational function. And therefore, we can talk about its singularity. And in particular, in this talk, we are supposed to be interested in the following value. So let us denote by this O of L prime to be. So this denotes the whole order of this normalized R matrix at this spectral point is equal to 1. So in this way, we get certain non-negative integer. And this is actually very important numerical invariant in the representation theory of quantum group algebra. So let me show an example. So when J is equal to SL2. So in this case, we have a so-called evaluation homomorphism from quantum group algebra to the finite type quantum groups UTSL2. So which corresponding to the operation specializing this loop variable to this fixed parameter A. And so, for example, so this quantum UT of SL2 has a two-dimensional vector representation. This is simple representation, and using this evaluation homomorphism, by taking the pullback along this evaluation homomorphism, we obtain a one-parameter family of irreducible, two-dimensional irreducible representation of quantum group algebra, and this is called the fundamental representation. And R matrix between two fundamental representations, say LA and LB. So this is easily computed as follows. So this is famous R matrix appearing in the 6-vertex model. So let me recall. Yeah, exact value is not so important, but it looks something like this. And where C is the ratio of spectral parameters. So C is equal to B over A. Okay. So in particular, so from this computation, we can easily see that O of LA and LB. So this is equal to 1 or 0. So it is equal to 1 if this ratio of the spectral parameter B over A is equal to Q square. Otherwise, it is just 0. So it is very simple computation. And when R matrix is regular, so it doesn't have a pole. So when, for example, when this B over A is not equal to Q square, nor its inverse. So in this case, we see that the tensor product representation doesn't depend on the choice of ordering. And this isomorphism is actually given by the specialized normalized. So if under this assumption, this R matrix is regular at z equal 1, so we can specialize the spectral parameter to get map from here to here, and the inverse map also obtained by specialized R matrix. So we get isomorphism, and moreover, we see that this tensor product is actually irreducible representation over quantum loop algebra. So this is a regular case, and otherwise, let's see what happens. So for example, let us consider the case of B is equal to A times Q square. So consider this tensor product. Then we can construct a map from here to here by the corresponding R matrix is no longer regular at z equals 0. But if we multiply z minus 1 to R matrix, then the denominator cancel out and we can specialize it. But this homomorphism is no longer isomorphism. This is non-zero, but this is no longer isomorphism. And its image is actually one-dimensional trivial representation. We can see easily. And let us see the kernel. So the kernel is three-dimensional, of course. Some kernel. And this is actually simple representation. So this is evaluation of three-dimensional representation of UTS2. And so this is kernel. And the co-kernel of this map is actually isomorphic to this same thing. And we can also prove that both short exact sequences are non-split. So this short exact sequence is non-split. So this trivial representation can be a quotient of this representation, but cannot be a sub-representation. This is again non-split. So as a consequence, we find that this representation, this tensor product is not isomorphic to this representation. So this is the singular situation. Okay. But in any case, if we consider the Grothendieck group, the class in the Grothendieck group of this tensor product representation, then we find that this is equal to the opposite class of opposite tensor product. So at the level of Grothendieck ring, we always have this commutativity. So this is Grothendieck ring. So at the level of category, it is non-commutative in general, but at the level of Grothendieck ring, it is commutative. And this is actually true in general for any G. And this was originally written down by the paper of Edward Frenkel and Reshetikhin. So this Grothendieck ring is commutative for any G. Okay. So now let me introduce some terminologies. So we say that two simple representations in this category strongly commute if the tensor product representation is again irreducible. So this is and this condition actually implies L and L prime commute because of this proposition. Okay. And we say that a simple representation in this category is real if L strongly commutes with itself. Okay. And with these terminologies, we can state the following thing. So this is a theorem, relatively recent theorem due to Khan, Kashiwara, Kim and O. So we assume that given two simple representations are real, then the following conditions are mutually equivalent. So the first condition is that L and L prime are strongly commutative. The second condition is that they commute. So condition 1 implies condition 2, but if we assume that L and L prime are real, then we have the inverse statement. And these are actually measured by the singularity of R-matrix. So this is equivalent to the regularity of corresponding normalized R-matrix in both directions. Okay. So in this sense, this polar order of normalized R-matrix measures the commutativity TBT between L and L prime in some sense. So or in this sense, and that's why I'm interested in this invariant. And so I want to compute. I'm trying to compute this invariant for general representations, but so far it has been no. So far it has been no. Only for some specific class of representations. So, for example, fundamental modules or some Kirillov-Reshetikhin modules. Okay. And the goal of this talk is the following. So, the goal of this talk is to describe this singularity of R matrix in certain monoidal subcategory called level 1 subcategory of C. And this level 1 subcategory is something very nice because it monoidally categorify a cluster algebra of finite type. And my goal is to describe this number in terms of categorification of cluster algebras. Okay. So now let me try to state my main theorem, but we need some preparation before that. So first we recall what is this level 1 subcategory, or what is this monoidal categorification. Of cluster algebra by using this level 1 subcategory. So first recall. So I want to define such monoidal category in terms of highest weight classification of simple representation. So recall there is a highest weight type representation. Sorry, highest weight type classification. Of irreducible object of our category due to Charlie and Presley. It says that isomorphism class is of simple representations, finite-dimensional simple representations are in one-to-one correspondence to the set of Dirichlet polynomials, but it can be alternatively stated as follows. So it is one-to-one in bijection with element from certain free commutative monoid generated by this symbol phi of IA. And here I is Dynkin node. For G. So I is a node of Dynkin diagram of G, and A is a non-zero complex number. Okay. And to introduce this level 1 subcategory, we have to assume that G is of simply Resto type, or type AD. And consider the following thing. So we take a function, integer valued function on the set of Dynkin nodes, and we call this is height function. If it satisfies the following condition. So if the difference of values of adjacent nodes is equal to 1 in absolute value. So if I and j adjacent, okay, and for each this kind of function, we define level 1 subcategory depending on this function xi and to be the cell subcategory of our category C, such that in terms of highest weight classification, the simple representation in our subcategory is 1-to-1 in 1-to-1 correspondence to the following thing. So we restrict the form of spectral parameter to be certain form of some power of Q, and this power is determined by this height function and plus height function or height function plus 2. So this is very small category, and it turns out that this. So cell subcategory means that we just consider the category, a smallest subcategory, which closed undertaking extension and subquotient. So it is completely determined by the its set of simple isomorphism classes, and it is from this definition. A priori it is unclear that this is monoidal subcategory, but it turns out to be monoidal subcategory. Okay, and this definition is due to Hernandez-Leclerc. And this is a very nice category. In the following sense. So this is what I mean by monoidal categorification of cluster algebra. So this theorem is due to many people, Hernandez-Leclerc and also Nakajima, and some people, including Kimura and Chin. So this Kimura and Chin's work is the most general one. And so it says that for any height function, so this Grothendieck ring of the level 1 subcategory. So this is commutative ring by Kirillov-Reshetikhin theorem. So this is as a commutative ring. This is isomorphic to something. This is cluster algebra. So, yeah. So cluster algebra is a certain commutative ring, which is defined associated to something called ice quiver. So I will explain what is this later. But this is a commutative ring, and this is a representation theoretically. This is natural isomorphism actually. So this isomorphism is given by so-called truncated version of Q character. Yes. This means truncated Q character. And this is not only an isomorphism of ring, but also under this isomorphism, the canonical bases of both sides get identified. So on the side of Grothendieck ring, of course, we have a natural canonical basis formed by classes of simple representations by definition. And on the other hand, so it turns out that so this is actually cluster algebra of finite type. And indeed, this the same type as G. So if G is type A, then this is cluster algebra. And for finite type cluster algebra, if we consider the set of so-called cluster monomials, then they give a basis. So for general cluster algebra, this is only a linearly independent subset set of this algebra. But in finite type case, this gives a basis. And under this isomorphism, these two bases get identified. So this is very nice isomorphism. And in particular, if we consider the subset of cluster variables, for example. So cluster monomials are certain monomials in cluster variables. And cluster variables can be seen as a prime elements in this set of cluster monomials. So this corresponds to the set of prime representation. So prime means that the simple representation which doesn't have any non-trivial tensor factorization. Okay, so we have this correspondence. So this is the meaning of monoidal categorification. And although it is not so important, but I will give the definition of ice quiver, where so starting from height function, we can height function determines the Dynkin quiver. So this defines an orientation on the Dynkin diagram, type AD Dynkin diagram, so that, for example, assume that I and J are adjacent in Dynkin diagram, and the height of I is less than height of J. In this case, we orient this edge in this way from J to I. Yes, so this is very simple rule. And so this is Dynkin quiver, and we add some frozen vertices here to this Dynkin quiver to get our ice quiver. So ice quiver is just so this is just a pair of quiver and the set of subset of frozen vertices. So this is something just a quiver, and this square node represents the frozen vertices. So for each Dynkin node, we attach a copy, its copy prime, and we add arrow from frozen to non-frozen. And for each oriented edge in original Dynkin diagram, we have corresponding oriented edge from unfrozen to frozen. But anyway, this is not important in this book. Yes. So for example, type A3 case. So Dynkin diagram is given by this. And as an special example with height function, we can take identity, for example. Then in this case, the Dynkin quiver is given by this, and this ice quiver is so this quiver with 6 vertices, and 3 of them are frozen. So this is so this is Kirillov. And my goal was to describe the singularity of R matrix in this category. And to do so, we need yet another categorification of same class algebra. So this is another kind of categorification called additive categorification. So this is a completely different kind of categorification which is given by quiver representation. So let me first introduce some terminologies. So let Q be a quiver. And we consider so-called decorated representation of this quiver. But this is a very simple thing. So this is just a pair. So M consisting of usual quiver representation. Yes, we are working on the field of complex numbers. And this B is decoration part. So decoration means that this is just a bunch of finite dimensional vector space. But I grade it. So for each Dynkin node, we have finite dimensional vector space for decoration part. And let me write this category of decorated representation in this symbol. Okay. So yes, so the decorated representation is something like this. And for each pair of decorated representation, so M and N prime, for example. Yeah. So we can define their E-invariant, so-called. So E-invariant is an analog of extension X1 between decorated representations. So this is, first of all, usual extension between quiver representations. And we also care about this decoration part by adding some additional term. But this additional term is very simple. So this is just by just a linear space of linear homomorphism from Mi to Pi prime. Yes. So this is just finite dimensional vector space. So this is invariant. And we have, we need one more terminology. So we say that M is rigid if invariant between M and itself vanish. So this is the condition analog to the vanishing of self-extension of quiver representations. Okay. And with these terminologies, I will state the additive categorification theorem of our quiver, our cluster algebra. This is basically due to Hernandez-Leclerc. And Derek-san, Ayman. Neumann Derbinsky, they are basically quiver, the researchers on quiver representation theory. Yes? Yes, so the vanishing of for vanishing of E-invariant, we require that this home space all vanish. So this rigidity condition is a little bit strong condition. Actually. No. Yeah, some of vi prime should be 0. So M is quiver representation. So it underlies on some high-graded vector space. Okay, quiver. So left Q. So it underlies on some graded vector space. So and this Mi is i's component. Okay. So for example, if Vi prime is non-zero, then we require that Mi is equal to 0 for the vanishing of invariant. So this is rather strong condition that this rigidity is. Okay. Any other questions? Okay. Clear. And we state the following result. So for any height function, there is a map from the set of isomorphism classes of object of this category of decorated representations. So each decorated representation, we have something in our cluster algebra. And this CC means cluster character. Some people call this as Caldero-Chapton map, but anyway, it is CC. And this satisfies some very good condition, a very good property. So first, this cluster character sends direct sum of decorated representation to the product of their cluster character. So something in some so this can be seen as some exponential map because it takes sum to product, and this induces, if we restrict this cluster character map to the rigid decorated representations, subset of rigid objects, then we find that it is in bijection with the set of cluster monomials. But we need to assume that the cluster monomials without frozen factors. So in our cluster algebras, we have some frozen vertices, and corresponding to these frozen vertices, we have something called frozen variables. But we, in this additive categorification, we need to forget about these frozen factors. Okay. And in particular, so because of this first point, if we restrict to some indecomposable object, then it is in bijection with cluster variables. Okay. So this is basically the statement of additive categorification. Yes. And from this statement, for example, in particular, we see the following. So in particular, so suppose that we two cluster variables x and x prime are given, and in additive categorification there is certain indecomposable decorated quiver representation, corresponding decorated representation. Then following statements are mutually equivalent. So first statement is that x and x prime belong to a common cluster. So this is equivalent to say that the product x prime is cluster monomial. Okay, and this happens if and only if the corresponding E-invariant between corresponding indecomposable representations vanishes. Because this requires that direct sum of m and n prime is rigid, and because of the additivity of this invariant. So yeah, so we require that this direct sum vanish, and so this, so this is equivalent to this condition because of additivity. Yeah. So yeah, and so this is additive story, and let us recall monoidal side. So in the monoidal categorization, so for each cluster variable we have some simple prime representation L and L prime, and because of thanks to Kankashwara-Kimura theorem, these two statements are equal to the vanishing of this O invariant. So the regularity of R-matrix corresponds to these conditions. So by comparison, so this E invariant and this pole order of R-matrix play same role here. So it is natural to ask if they coincide or not. And finally, I state my main theorem. So we assume that L and L prime. So given two simple representation in our level of subcategory, then we have the following equality. So the O of L and L prime is equal to the dimension of E of M and M prime, where M and M prime are some decorated representation which are rigid, such that the cluster character of M is equal to the truncated Q character of L, and cluster character of M prime is equal to truncated Q character of L prime up to frozen factors. Okay, so this is my main theorem, and And I have to emphasize that the left-hand side is quite difficult to compute because we have to know the information of R-matrix, and we have to try to compute R-matrix, but it is in general very difficult. But the right-hand side is actually, this is just an extra one between quiver representations, and this is very easy to compute. So the right-hand side is, at least for me, this is much easier to compute. And there is a combinatorial way to compute this right-hand side. So I think this gives a good enough description of left-hand side. So I stop here. Thank you.
Thank you. Have questions?
First, can you just repeat when you define the correct representation on the left board there? This M and V, can you comment who they are, like arbitrarily chosen? Or when you write vector, do you mean fundamental representations? So just curly M equal MV. So you say.
So sorry, you want some examples?
How straight M and straight V are chosen for the correct representation? Can you comment one more time?
So you do not see the naturality of this kind of definition?
I mean, is V arbitrary? Like for every node of Dynkin diagram, you have any representation you like, or what?
You do not believe that there is enough rigid representation or something like that?
Just something.
Okay.
Okay. Okay. Then the actual question is. So you know when we have cluster algebra, we have mutations, right?
Yes.
And there are mutations that preserve Dynkin diagram. You just change orientation.
Yeah, on the quiver side we can say.
Yes, this might be well reflections hidden for you. But also there are more interesting which make it, let's say, for S3 example, it will be triangle, right? You will change connectivity of the graph. I mean, if you do mutations that from the line, when you can make orientation, you make a triangle.
Sorry, this is.
Yes.
So this is a fixed Dynkin diagram determined by height function, and basically, yeah, I agree that by applying mutation, the orientation of quiver change. But in this additive categorization theorem, so actually this refers to the initial quiver.
No, but my question, if you apply mutation, and that not only orientation changes, but it changes topology of your quiver, it becomes like loop instead of a line. What is the corresponding for happening with your, well, I suppose, what was this object called? Well, I mean, like objects in your category, right? This is subcategory. So what happens there?
Yeah, so this, how to say, both construction, monoidal categorization and additive categorization, both depend on the choice of initial seed of cluster algebra. And this Dynkin quiver and this iced quiver here refers to the initial seed. So we have to fix this anyway. And if, for example, if we change this height function, we get some different monoidal category and different category decorated representation of quiver. Yeah, of course we can compare them, but they are not literally equal. So.
No, my question is different. When you have Dynkin quiver, you have cluster algebra.
Yes.
Then you know that you can make mutations at the node of the quiver.
Notation?
Mutations.
A mutation. Okay,
later.
I'm sorry. Yes.
If your question is short.
Yeah, sorry, so can you explain a little bit how to prove your main result?
I did not say anything about the proof, but my proof here is using some geometric representation theory, using Nakajima's quiver variety for this category.
Yeah, maybe I'll ask you later.
Yeah, if you are interested, then I will explain it later. Yeah.
Okay, let's speak If short question.
Yeah, that will wait. No worries. sorry. Yeah, so I got a quick question. So
Yes.
about real modules, do you have a description of real modules?
No, it's difficult to describe real.
Can you give an example of non-real module?
Yes, there are plenty of examples of imaginary modules.
Thank you.
Yeah.
That was quick.
Yeah.
Thank you. So if you have more questions to speaker, you can ask it during welcome party.
Okay, thank you.
So thank you for talk.